These notes are on the difference of two squares and perfect square trinomials. Earlier in the year, we did a lot of factoring of trinomials and binomials. And there were two patterns that emerged that the nice thing about noticing this pattern is that you don't have to spend a lot of time thinking when you're given problems that have this pattern. You know the pattern, so you can simply perform the correct matching equivalent pattern. So one of them is a difference of squares, meaning I have two squares, two perfect squares with a difference, subtracting. And the factoring pattern there is going to be the square root of the first term minus the square root of the second, and the square root of the first plus the square root of the second. The other pattern that we would have noticed is when I have the pattern of a perfect square trinomial. And this is the pattern that we saw a lot when we were completing the square and we were getting parabolas from standard form into vertex form. So that pattern is that the first term is a perfect square, the last term is a perfect square, and the middle term is 2 times the square root of the first and the last. And that factors to be a plus b, so the square root of the first plus the square root of the last squared. Or minus, depending upon if the perfect square trinomial has a positive or a negative here. So let's look at a few examples. In my first example, I'm given only two terms, so I'm looking for that if it's the difference of two squares. So is the first term a perfect square? Yes. Is the second term a perfect square? Yes. Is it a difference? Yes. Which means my pattern is going to be the first term square rooted minus the second term square rooted times the quantity, the first plus the second square rooted. Our next example has three terms. So now I'm wondering if this is in the pattern of a perfect square. Yes. Perfect square, yes. And if this is 2 times the square root of the first times the square root of the last, and it is indeed. Negative 16x is indeed 2 times x times 8. Noting here that, of course, that I have a minus sign here, meaning that my 8 is a negative. So I have x minus 8 quantity squared. Next example also has three terms, so I'm going to check here. Is my first term a perfect square? Yes. Is my last term a perfect square? No, it's not. This 12 here is not a perfect square, even though the y squared is. So this one is not possible as far as our perfect square and perfect difference of two squares and perfect square trinomials. And it turns out that this one is not possible for any terms of any kind of factoring either, because no two numbers that multiply to be 12 are going to add to be 6. Next example, a little bit more complicated. I have a trinomial, so I'm looking for that perfect square trinomial pattern. Is my first term a perfect square? Yes, it is. 5x is the square root of that. Is my last term a perfect square? Yes, it is. 7y is the square root of that. And is my middle term 2 times the square root of the first times the square root of the last? So we're going to need to check that. So 2 times the square root of the first times the square root of the last. So is 2 times 5 times 7 times x times y 70xy? And it is. So I have 5x plus 7y quantity squared. Our last example has only two terms, so I'm asking myself if this is a difference of two squares. So I see the difference right away. So now I need to check that both of these are perfect squares. And they are. 100x squared is the square root of that is 10x. And 9y squared is a perfect square. The square root of that is 3y. And my pattern is to have 10x minus 3y and 10x plus 3y.